is very different from what a stars might be. So probably very regular, whereas these will be quite fluctuative. And as we all know, there are 8 planets in the solar system. Um, so, for example, if you wanted to see Saturn, so if you were in Chennai and yesterday you wanted to see Saturn, you would be very lucky because Saturn's rise time was around 12 a.m. or 11:40 a.m. to be precise. So, because it was 11:40 a.m., you could just go up around 12 a.m., 12:30, 1 a.m. maybe, and look at the night sky, see, okay, um, Saturn will be actually visible. But for other planets, let's say, for example, Jupiter, the rise time was 4:13 a.m. today. And with the light of the sun, I don't think anybody is going to be able to see Jupiter, even if you do decide to wake up that early or stay up the entire night to see one planet. Um, but how do you know which object in the sky is Saturn? So there's a very useful app that I would like all of you to install to get started on observation astronomy, and that is Stellarium. Stellarium, Stellarium. It's an app that's available on Android, iOS, and even on Windows. And basically, it allows you to point your mobile phone to any point of the sky, and it will reveal to you what objects are present in your field of view. So if you point your camera at one point in the night sky, it will tell you all the objects that lie in your field of view. So if you wanted to basically see Jupiter, all you have to do is wake up at the correct time, obviously, and uh, look around with your cell phone until you basically saw Jupiter. And since Jupiter is a very bright object, you'll be able to notice very easily. Um, so that's about some of the planets. Obviously, the moon and the sun are always visible. And then we come to probably the next easily visible object in the sky, that is stars. So stars again are very easy to spot. Um, if you want to spot specific stars, probably use Stellarium. And if you want to get to know about specific stars in the night sky, also use Stellarium. So point it at a star, it'll tell you everything there is to know about the star, the size, luminosity, distance, everything. And stars appear as point objects in our uh, in our sky because they're so far away, yet their apparent size is very small. So even if you use a telescope, you will still see a point object and you won't be able to notice any details, right? So stars appear as point objects in our field of view, and these are very easy to spot. So some very bright stars you'll be able to see in the night in the winter, for example, are Betelgeuse, Sirius, and nowadays you can probably see Arcturus and a couple of other stars. So that brings us to probably the next easily visible thing, which are nebula. So nebulae are basically giant clouds of dust and gas, um, just held in by their, gravitational weight or gravitational pull. So these nebulae are visible from Earth, but you do need to be able to um, have a sky with less light pollution. So you should be able to have a clear view of the sky and not be obstructed by light pollution like in major cities like Chennai or Bangalore, Mumbai, Delhi maybe. So these nebula are not exactly visible in the night sky to the naked eye, but you will be able to see like a hazy, fuzzy looking uh, patch, a very small patch in the sky. And if you know the exact location where to look, you'll be able to figure out that this is a nebula. So this picture, this is the Orion Nebula. And when you look in the night sky, this is probably not what you will see. So some of these details have been exaggerated because when people do astrophotography, they like to capture all the details, even the details that are visible in only in infrared or um, non-visible spectrum. They like to capture those details also. So you will probably not see anything even close to this, even if you look with a telescope. And this is probably the most famous, easily visible nebula in the sky. But don't get discouraged. nebula are very beautiful, and you can see them provided you look in the correct direction. The next thing that you can see brings us to the bottom right corner, called star clusters. So again, star clusters are basically stars that are held together in certain formations by their own gravitational pull. So there are two types of star clusters. One is what you are seeing right now. This is the Pleiades star cluster, and it's very famous. It's called the Seven Sisters. Um, it comprises of 7 stars, and this is called an open star cluster. So these are relatively young and consists of very few stars. And as opposed to this, there are globular star clusters. So globular star clusters are star clusters that are very old, have many hundreds of thousands of stars even held together under their own gravitational weight. And a very good example would be M13 globular star cluster. So that is present in the Hercules constellation. And basically that star cluster consists of hundreds of thousands of stars, whereas this consists of 7. So you have different, so to say, sizes and brightness, everything of star clusters. So this is the most easily visible. Again, this is probably not very visible with the naked eye on a normal day, but if you use a good telescope, and or if you get a sort of good night sky, then you'll be able to maybe see it with the naked eye or locate it. Um, then it brings us to the probably um, most commonly known galaxies, right? The object in the dead center of the frame. So galaxies, as everyone knows, are just uh, a mass of about 100,000 light years, 200,000 light years, very large span, uh, a very large size, and it consists of all the objects that we can see in the night sky. And this is obviously also held in place by the gravitational pull. And so at most galaxies, there is a black hole at the center. There is also a black hole at our center called Sagittarius A. And uh, galaxies are visible in the night sky. For example, on a good sky, you might be able to see Andromeda galaxy with the naked eye, but it's very hard to see it on a with the naked eye. With a telescope, you will probably able to see it more easily. Um, Again, that is probably the closest galaxy to us. It is about 2.5 million light years away, and its size is about 200,000 light years. But it is still moving towards us, which means the Milky Way and the Andromeda galaxy will eventually collide. And this collision will happen billions of years later when we all perished. But this collision between the Andromeda galaxy and Milky Way will eventually happen. And the I think the Andromeda galaxy is moving towards us at a speed of about 140, 120 kilometers per second. Very, very fast, faster than anything we ever sent out. So Voyager 1 was the fastest we ever sent out into space. And that is probably moving around 17 kilometers per second. So about 7 or 8 times the speed of that. Okay. So what about constellations? So there's basically in the northern hemisphere, we can kind of think of the um, sky at two different times, the summer sky and the winter sky. So first of all, let's figure out why do constellations, you know, exist? Why do we have these, random stars that kind of look to be in a formation but not really? And why are they given weird pictures? Like, how does the Big Dipper look like a big bear? And how does the Little Dipper look like a small bear? And who came up with these? So these were actually our ancestors, and they came up with this because they had no other way of determining direction. This was their only way of navigating on Earth. They used to keep track of stars, and the best way to keep track of stars was that they assigned these pictures, and this they gave inanimate objects um, life. It was easier for them to remember these and keep track instead of having to um, look in the sky and figure out from scratch every time. And some of the most important constellations also guide us to some of the most important stars. So Big Dipper is probably the most commonly known constellation. It's called Ursa Major also, and it's it's a very commonly known constellation. Right near it is the Little Dipper, also called Ursa Minor or Small Bear. So Big Bear and Small Bear are very close to each other. They look kind of similar in the sense that they both look like this kind of trolley cart and being pulled by a rope, right? Um, but the Little Dipper guides us to a very, very important star called the Polaris. So the role of the Polaris in the night sky is very, very crucial, as we'll see later. So Polaris guides us to what is almost perfectly north. So the thing about Polaris is that the height of Polaris, the altitude, never changes in the sky. And this can only mean one thing, and it means that it's almost exactly at the axis of rotation of the Earth. It lies on the axis of rotation of the Earth, which is why even though the Earth rotates, the position of the Polaris does not change in height, but only along the other coordinate. So height or the altitude, if you look down at the horizon, you would always have to turn your head the exact same number of degrees every day in the night sky to be able to look at Polaris. So it guides us through the North Pole or the true north, to so to say. We also have a lot of other constellations like Scorpius, and we get the summer triangle by following these three very bright stars, Altair, Vega, and Denab. These are almost always visible in the night sky. That gets us to the winter night sky. So winter has probably some more famous things. So the most famous being the Orion constellation. So Orion is the hunter constellation. As you can see, this is kind of the shoulder. This um, there's a bow here. We have the belt of horizon, the sword, and these are kind of the hip or the legs, whatever you want to say. The important thing for us is this belt. And how to locate this? We see this bright red star, Betelgeuse. And just below it, you will see three sort of diagonal, very closely spaced stars. And this is called the Orion. Now take the middle star and go right down to the sword. The sword, if you zoom in very carefully, if you look carefully, the sword is actually where the nebula is. So there are about two or three stars there, but in the middle, in between those two, three stars, there is a nebula. And that nebula is the Orion Nebula, very famous nebula. And even on a clear sky, you will be able to look there and see a hazy, fuzzy region. And that actually is the Orion Nebula. That's not clouds or anything random in the night sky. That's the Orion Nebula, and it's the most easily visible. So next, following from this belt, we go all the way up and we take a slight detour to reach this another bright kind of red star, Aldebaran. And when we reach Aldebaran, we can go again, take a small detour and go straight. You get Pleiades, the star cluster we were talking about. So these are probably Pleiades, star cluster, Orion. These are the most famously known things that you can see in the night sky, even with the help of a decent telescope. We also have the Andromeda Galaxy M31, like I was talking about. And this is very, very far away, but because of its sheer size, it is the closest galaxy to us also. We can see it in the night sky. The other galaxies are pretty hard to see with the naked eye. So moving on, we'll talk about the telescope. So all of us know what a telescope is, I'm sure. Basically, it helps us to see objects that are very, very far away in the night sky, right? Um, but how does the telescope work? What is the mechanism behind the working? And when you're looking to buy a telescope, for example, what are the parameters that you should consider before buying one? So let's have a small inspection of the telescope first. So how does a telescope work? So basically, telescopes are of two types. One is a refractive telescope and one is a reflective telescope. So in 11th, 12th, we study refractive telescopes, but most telescopes are not of this kind. So most telescopes are not made with lenses, and there are multiple reasons why. And one of your questions that will be uploaded in the assignment is related to this. So you will be asked about why a refractive telescope is not used as much as reflective ones, right? So refractive telescopes are generally very outdated, and you will only see them in kids' toys. So you those ones you get online or in store, those ones might have lenses, but any good telescope that you see on the market will that's expensive will probably be reflectors. So one of the most important kinds is the Newtonian reflector, which has a primary mirror, a secondary, which is at 45 degrees to the axis of the first mirror, and then you have your uh, basically where you put the eyepiece, right? Now, where is the secondary mirror kept? What is the function of the primary mirror? All of that I'll talk about. So when light comes from a very far object, basically the primary mirror does all the light and it reflects it onto its focal plane. Now, just inside the focal plane rather, we place a secondary mirror at 45 degrees angle so that the light gets reflected and it comes onto the eyepiece, right? This is how we're able to see objects in the night sky. But this doesn't tell us what kind of objects deserve what kind of telescopes, right? So there's basically two parameters that mainly govern a Newtonian telescope. The one is aperture. Aperture refers to this diameter. I hope my cursor is visible. This diameter of the telescope. It governs how much light enters your uh, your telescope per second. So if you shot a 2-minute clip with a wider aperture versus a smaller aperture, the wider aperture would literally appear brighter. Sometimes this is what you want, and sometimes this is not what you want. Whereas with a larger focal length, so focal length and length of the tube are kind of used interchangeably with Newtonian reflectors and with almost all telescopes because um, as you increase the focal length, you're effectively increasing the length of the tube as well. Um, and they increase almost proportionately. So online, you will probably length of tube and focal length will be used interchangeably. Don't get confused, they mostly refer to the same thing. So focal length, an increase in the focal length means a smaller field of view. So if you're looking to capture a planet, for example, you want a very small field of view because the planet in and of itself is not very large. It takes up a very, very, very small space in the sky. You just want to focus your details on that. So you take a very long telescope that gives you a small field of view, and because they are already bright, the planets are pretty bright in the night sky, you can see it even with the naked eye, means you don't need a very wide aperture either. You can use a small aperture. So the aperture and the focal length govern what kind of telescope you should buy or what kind of telescopes you get. So there is something called the F ratio. F ratio determines um, the focal
Hello, sir.
length
Am I
by the
audible?
aperture. Yeah, you're audible. Yeah.
Sir, I had a question regarding the previous topic, the Polaris.
Uh-huh.
So I've heard that the Earth's axis wobbles slightly. It moves a bit.
Yeah.
So does it affect how is the Polaris always stationary whenever we see it in the night sky?
Yeah. So there is a little bit of precession and so to say wobbling of the Earth's axis about the Polaris, but over a day or two, over a few nights, this effect is not very noticeable, right? So this effect is noticeable over large periods of time. And when we come to measuring the celestial coordinates an object in the sky, for thousands of years or for hundreds of years, we don't need to work much on changing them, right? So there is a little bit of wobbling, there is a little bit of precession, but effectively, this is almost zero for one night's observation, 2 nights, even a few nights, or a week, months. This effect is almost negligible.
Okay, sir. Thank you. Also, another question. I've heard that there is also a southern Polaris in the southern hemisphere. Can you confirm?
I'm not exactly sure about that, but there might be. But
Oh,
you only need realistically one of them to keep track in the sky, right? If you think about it, you only need one star that tells you where the north is. If you figure out one direction, you can figure out west pretty easily.
thank you.
Yeah. All right. So coming back to this, the F ratio tells you the focal length divided by the aperture. Effectively, it tells you um, whether your scope is really good for deep sky observation or not so good. So, for example, also when I say deep sky, I mean objects that lie far away from Earth, not planets, the stars, galaxies, nebulae, star clusters, all of those things, right? Um, when it comes to observing those kind of objects, you really want a fast telescope. A fast telescope means one with a smaller f ratio. So, for example, the stuff we get on the market, this is something I looked up, right? First thing I look up, I say telescope available to buy for beginners, something this came up. And then I calculated the f ratio, it came out to be 11.66. Now, as you can see, it's very long and its diameter is very small in comparison to its length. This is not something you would see at a professional astronomer's, backyard. But there's something that's available online. It's easy to purchase, it's cheap, and it gets the job done for small, like the planets, moon, um, all of that stuff. It gets the job done for that. So when you're looking to actually capture deep sky objects like nebulae, star clusters, galaxies, these objects are very, very wide in the sky. And we don't see these as very wide in the sky because of light pollution, but they actually are extremely wide and they capture a very big field of view. So when it comes to astrophotography, magnification is not as important as getting the entire field of view of the object in the frame. So if you're looking at a nebula, you don't want to magnify too much because the nebula is so wide, you will lose out on details if you go for magnification. Instead, you would rather focus on getting a wide field of view and capturing as much light as possible, right? So it gets us to what kind of scopes to use for what kind of objects. So, like I said, for planets like Jupiter, a narrow and long scope will be just fine because these are inherently bright enough, which means the aperture can be small. And like I said, um, the field of view required for this is pretty small. So, a smaller field of view means a longer telescope. Same goes for a star. Most stars are bright enough, which means you don't need a wide aperture to capture too much light. And this goes for most stars. But if you really want to focus on one that is not so bright, maybe use a slightly wider aperture. So this brings us to star clusters. So the object in the top right corner is the star cluster. So this is the M13 star cluster I was talking about, a globular star cluster. This is very, very wide. This is light years in diameter, right? How do you make sure the entire width of this star cluster is captured? If you go and say, no, I want to go for maximum magnification and use a very long scope, you will miss out on a lot of details. You will only be able to capture a small region, right? Instead, what you should do is opt for a short telescope that gives you a wide field of view. And because these are very far away, these are very faint, right? These are not as close as brightly illuminated stars. So these star clusters are very far away and they're very dim. So you want to use a wider scope to capture these. Now we come to nebulae again. So like I was explaining, nebulae is just a collection of like a lot of dust and gas spread across um, a very wide region of space. So light years, hundreds of light years, sometimes you maybe. Um, I think one of the nebula, the Crab Nebula, is very wide. It's like a couple of hundred light years or 1,000 light years wide. So capturing all the details requires a very short scope. as short as possible. And it also needs a very wide scope, right? Um, so that you can capture all the brightness even with a short exposure. Again, same when it comes to galaxies because they're very far away. Except the Andromeda galaxy, um, sorry, except a few very distant galaxies, galaxies are also pretty wide. So, like I was saying, the Andromeda galaxy is about 200,000 light years wide. This is extremely wide, right? You need a short scope, you need a wide scope to capture its brightness. And when it comes to stuff like the moon, a normal telescope on the market is fine, like very narrow. And if you're looking to capture the entire time of the moon, maybe something shorter, but if you're looking to capture particular craters, you can go for a longer scope. So this is all well and good, but like I said, you're trying to, if you're looking with your eyepiece at least, you're trying to look at what is the maximum magnification that is visible, that is possible to get, right? Not the maximum, but you're at least trying to magnify to some extent. So that is given by the focal length of the telescope divided by the focal length of the eyepiece. Now, this calculation is actually done even when we study ray optics in JE days. We do this calculation, and it comes out to be f of the telescope by f of the eyepiece. I don't know how many of us remember it, but the magnification is exactly that. And the calculation is pretty simple. I won't go into it, but you can look it up online. Um, you might see like two lines. So you see like this purple line and this green line, right? So effectively, you can see that the focal point of both of these light rays is not the same. Or though this purple line seems to like have its focal point at this x, the green will have it somewhere around here, which is a little bit away from it. And as you give more and more angle, so if all your rays are paraxial, sure, but in star clusters or nebulae, we cannot work with the assumption that all the rays coming from the light are parallel. So there will be light coming from the edges, light coming from the center, light coming from the top, and these will have different angles. And for example, for a star, that's not the case. A star is small in size compared to nebulae and all that. So all the rays can be assumed to be paraxial, but for nebulae, they can't. We can't assume that all the rays will be perfectly all the rays will be perfectly parallel to each other. So this effectively gives you this green and purple lines. They give you uh, basically tells you what is the field of view. How many uh, things can you see at once in the night sky, right? This field of view is determined by the focal length of the telescope. And again, we've talked about this. So the higher the focal length, the lesser the field of view, which means that at the eyepiece, you will be able to see lesser and lesser things. Okay, this brings us to coordinate systems. What are coordinate systems and why do we even need them? Well, think about it like this. You see a star in the sky and your friend is in Bangalore, let's say me, and you want to tell him, "Oh, I see a really bright star in the sky. I want you to see it. I want you to take a photo, um, or whatever." You just want to communicate to your friend or to anybody in the world that you see a star and that location is where you see it. How do you communicate this location to your friend? We use a celestial coordinate system. So one simple, very simple way of looking at uh, a star is by saying, okay, let's just look at the horizon, which is the farthest point you can see basically. Um, it's given by the tangent plane at uh, your your position basically. If you can see on the right, this tangent plane effectively determines your horizon plane, right? So on the left, you can see this horizon plane is given by a top view. This is what your horizon looks like. You say, okay, let me look at the horizon and just turn my head up. As soon as I turn my head up and I see the star, that's my altitude. So it effectively gives you this. Sorry. I think there's some problem. But while it fixes, effectively the altitude is given by how far up you look to make sure that you see the star. That's your altitude. Then you say, okay, what about how far left or right I should look? Well, we figure out, let's say you figured out where the north is, right? With the help of this pole star, like we were talking about. We figured out where the direction of north is. How far east do I have to look to figure out where my star is, right? So that is given by the azimuthal coordinate. So two coordinates are enough to give you the direction of the star. Whereas if you want the distance, there is no simple way of figuring it out. You would have to use some other sort of metric. But to figure out the direction is very simple. You use two coordinates, the altitude and azimuth. Um, sorry. This- Sorry for the delay. Yeah. So as we can see, how far up you look is the altitude, and how far east you look is the azimuth. Now, remember that this altitude is not given by a fixed point in space. It is completely dependent on your frame of reference. How far up you look depends entirely on where you are standing. So you on the right, you can see, for example, if you are standing at this position, a star might be exactly head straight up at the zenith, 90 degrees up, right? Um, but there also might be a case where you might be standing exactly on the equator, right? Um, in this case, you're probably not directly, the star is not directly overhead. So as you can see, the altitude is very much dependent on where you are standing, and so is the azimuth. So this is again a 2D cross section, but extrapolating it to 3D, if you are, for example, in Africa versus somewhere in South America, the amount you would have to turn right or east, for example, the amount you would have to turn east from the pole star would be entirely different because you're in two different places on the earth. So because this frame of reference is entirely dependent on you, astronomers cannot really use it as a proper coordinate system. It's very difficult to keep track of a person's location and the time and everything. This doesn't even take into account the spinning or the rotation of the Earth, which means as the axis of the Earth rotates, both altitude and azimuth will change, right? And this is fairly simple to see. Um, this is a bad coordinate system in short. So it is okay if you just want to tell your friend who's beside you how much up and like up, down, left, right to look, but someone who's far away in another country maybe it's very hard. That's why we have a better coordinate system. This coordinate system is called right ascension and declination. This is what every astronomer uses. Now, if you go on the internet and do a simple Google search for any star, go on Wikipedia. One of the first things you will see is the location, and it'll tell you this much RA, this many degrees RA, or and this many degrees declination. What does that mean? Let's have a look. So basically, RA and Dec says instead of fixing the frame of reference on the observer, why not fix the frame of reference in space? Which means the point from which you measure 0 RA. So in that case, it was the north, um, right? Uh, it was the North Pole, but as you see it, right? Here we say, let's fix the 0 RA at this point. What is this point? It is the intersection of the ecliptic and the equator. So ecliptic is basically the apparent path of the sun around the earth if you consider earth to be fixed at one point. So we all know that the sun is stationary, almost stationary when we look at it, um, or rather the earth revolves around the sun basically. But if you say, no, I want to fix my frame of reference and say I am stationary, then it appears that the earth is stationary and the sun revolves around the earth. So the apparent path of the sun around the earth is called ecliptic, right? Now, the intersection of this ecliptic and our equator, our normal equator, gives you this vernal equinox. And you'll see that it intersects at two places, and we take any one of them arbitrarily to be the point of 0 right ascension, 0 hours. So basically, this point is completely independent of your location. So if you were in South America or Africa, you would still measure 0 right ascension from exactly this point. And when it comes to the declination, you just measure it from the equator. From equator, imagine you are standing exactly on the equator. What is the altitude of the star if you're standing at the equator? That gives you the declination, right? Simple as that. And these two coordinates are fixed. Like it fixes the star's coordinates, which means it takes into account the Earth's rotation. And it also takes into account people might be at different places while viewing the same object. So because these are completely fixed, astronomers use these and we can tell, okay, like this object in the sky has this RA and this declination, right? So there's another problem though, is we cannot use this for planets. Uh, does anyone have any idea why we can't use this for planets? Like why this system might not work for planets as effectively as it does? You guys can unmute and talk anything else. Okay, looks like there's no answers, but
Planets don't move around the ecliptic. They are nearer to us, and they do have an own movement of their own. They are not fixed like stars.
yeah, exactly. Thank you for the answer. So basically, as looked from Earth, stars are fixed in place. Over thousands of years, these things don't change, right? And stars are almost fixed in space, and their only movement is around the Milky Way, which is kind of negligible over our desired time frame, right? Which is a few hours, few nights, days, maybe even weeks. So these stars don't move around much. But planets are literally orbiting the sun, the same star we are orbiting. Their RA and Dec does not say the same because they are changing at every time. Even from night to night, their RA and deck will change. So this is a problem, and this is why we use it mainly for deep sky objects. Deep sky objects that are very, very far away and their apparent movement is very negligible, right? Same goes for the moon. The moon would have very different RA and deck every day. So the way it works is the north celestial pole is kind of very close to the Polaris, and the altitude, when we measure the altitude of Polaris here, we can see it is always the same because the axis of rotation of the Earth is leaves the altitude completely independent. You can see that this circle is where you would be moving in, right? Altitude of the Polaris is almost never changing. So that is why we use it, as you will see in tracking of stars. So this was the vernal equinox and how the celestial coordinate system is used, right ascension and left inclination. So why do we have to use this? Why do we need a fixed coordinate system? As in, it's doesn't even matter if we're taking a single shot of the sky, right? Because we can always just point it, like let's say you have a star in mind and you want to capture just a single shot, like as little exposure time as possible, one single frame, right? How do you capture it? Just point it up at the sky, take a photo, and you're done. Why do we even need these weird coordinate systems that are so complicated? Just look up, look left, right, and you'll get it. But there is a problem, and the problem is that these stars or stuff that you want to capture in the night sky, they are not capturable with a single shot, which means you will probably not get a very good image with just one single snapshot, right? And the thing is, when it comes to deep sky objects, they're very, very, very faint. They're barely visible with the naked eye. If you try and take a photo, even if you zoom in, you will get almost nothing. What you have to do is take multiple photos. Take multiple photos and stack them on top of each other. And then after post-processing, you mess with a lot of settings. Then is when you get a good photo, right? To bring out all the colors and to bring out all the things that were there in the photo. It takes a lot of exposure time, sometimes minutes, hours even, and probably not hours, but a couple of minutes. And generally in normal photography, we don't do that. Normal photography, the max we go for exposure time is 1/60th of a second, 1/30th of a second, that kind of a thing. More than that, the object kind of moves out of frame and we don't get a nice picture. So when we're taking a normal photo, we get enough light emanating from the object so that the exposure time doesn't have to be high. But from a deep sky object, this is absolutely not the case. We need multiple seconds of exposure. And when we do this, if you try to keep the camera or telescope fixed in frame, the object will just move out of the sky. It will simply move out of the sky because of the rotation of the Earth. So although the star is fixed in frame, it kind of moves out of frame because of the rotation of the Earth. And you can see this in this video. So look at this thing we're trying to track. It is literally moving around in circles around the Polaris, right? And to make it worse, you can see here, every star is moving at different amounts, left, right, up, down, and it's almost impossible to keep track of how each star is moving without knowing prior, right? You can't just keep moving a telescope manually all the time. This is why we need to track a celestial object to make sure that this object stays in our desired field of view and we can capture it multiple times, multiple seconds of exposure. And this seems pretty simple. If you look at this, you will see that the Polaris is at the center of all of these spirals. These all the other objects seem to be going around in circles around the Polaris. So somehow maybe what if we have a um, a mount on a telescope such that if you point it at the Polaris and if it's aligned properly to the Polaris, then maybe we just need to fix the radius of the star, and then we can move the axis of the telescope to match the angular frequency of the Earth, the angular rotation of the Earth, right? That way we can keep our star fixed in frame, and we can do it using a motor instead of manually having to move our telescope. So first, let's look at the alt mount, the altitude and azimuth mount. It gives you 2 degrees of freedom, right? It's a very simple mount. It basically keeps the telescope fixed in place. You're tightening screws to make sure that the telescope stays fixed here. So this is the azimuth, this was the azimuth, and this is the altitude, right? Up, down. And you can see this, he literally tightens the screw, make sure that the telescope does not move anymore. But when you do that, when you say, okay, my telescope is fixed now, how do you, so to say, move it? And even if it is balanced, in this case, it might not be balanced, but if it is balanced, since there are no motors or um, automate, like an axis you can automate, you cannot move this without using your hands, right? So a better thing is the equatorial mount. So this looks very daunting, I'm sure, but we'll break it down step by step and we'll figure out what everything is. So there's again 2 degrees of freedom that we have for the equatorial mount. One is the RA axis, like we talked about, and you can see that this person is moving the telescope about the RA axis. And then we have the deck axis. This fixes the declination, right? Now, this is all well and good, but you might also see something very peculiar here. These are the counterweights. You see these weights present here? Why are they there? So effectively, this scope has to be balanced properly manually. So these counterweights are attached so that when you're balancing along the RA axis, the torque of the telescope about the RA axis is balanced by that of the counterweights, right? And the same goes for the deck axis, which is balanced by moving the telescope up and down these sliders. So these sliders, so to say, like these holders are fixed in place, and you slide the telescope up and down to basically make sure that it's perfectly balanced. The torque about the deck axis is perfectly balanced. It's zero. So you can see that this RA axis and deck axis, and you also might see this. To make it more complicated, this equatorial mount sits on top of an altaz mount, on top of an altitude azimuth mount. So why do we need this? So I was talking about in the previous slide, we have to sort of polar align our scope so that um, we can use the North Star to track the movement of the other stars. How do we do this? If we align the RA axis using this altaz mount, using this altitude and azimuth mount, align this RA axis to the Polaris, right? If you align this RA axis to the Polaris such that um, you see this, you see this sort of uh, like eyepiece here. If you take off this cap, you will see that there's a small space. In that small space, if the Polaris is present, you can assume that your RA axis is perfectly aligned. And if you don't want to go through the trouble of doing all that, there is literally an altitude altitude like knob here. Set that altitude knob to the latitude of your place. So like we were talking about in, I think, this slide, we can see that the pole star has an altitude of your latitude, or 90 minus latitude, doesn't really matter. But that latitude stays fixed at all times. So um, your latitude will literally give you the pole star's altitude. So because the pole star's altitude is always fixed, all you need to do is go ahead and fix the azimuth. And fixing the azimuth, you can use a compass. You can also try and roughly point it along the pole star. Once that is done, your RA axis will be perfectly aligned to the pole star. All you have to do now is move like in the deck axis to by the amount of radius of the star, or radius away from the star. So in this case, it would just be like so. Let's say you're tracking the star. Move this much radius with your deck axis, and what you do is you say, okay, let me put a a motor on the RA axis. So the motor on the RA axis will make sure that this entire motion is encapsulated. You just have to make sure that the rotation of that is the rotation speed is that of the Earth's rotation speed, so that that effect of the motion of the star around the Polaris is captured, and your object stays in that exact field of view. I hope that makes sense. So that is why we need equatorial mount, and that is why we need to track objects, and that is how we track objects. Again, exact tracking and exact how it works, you can look it up. It's a little bit complicated, and it's better explained when you're offline and actually seeing a telescope, which is why I didn't go too much into it. But it is very helpful to use an equatorial mount, and that's how it works. So now we come to astrophotography, right? How does normal photography and astrophotography differ? So, like I said before also, the amount of light coming from an object in the night sky is very, very less in the amount of light coming from a normal object is very, very high as compared to that of a celestial object or a deep sky object. Now, what does that mean? You need to take longer exposures, few minutes, few seconds, depends. But with that, we also have to understand that there is so much noise, right? When you take longer exposures, there is increased amount of noise. And also, not to mention the light that is passing uh, through that, the entire light years or whatever amount of distance also has to additionally cross your atmosphere, which is very turbulent and is horrible. Which is why we mostly don't see any of the objects in the night sky, right? Low amount of um, light is bad enough. There's other factors that add to the noise also, right? Additionally, like I said, the object keeps moving, which means you have to track it. So how do you make sure you can encapsulate all of these things and get the correct exposure, get enough frames while also minimizing the noise? So there's something called stacking. And stacking means take multiple images and literally stack them on top of each other so that the signal keeps increasing, whereas the random noise, it goes out to be zero. It almost, if you have like a random noise, let's say one reading is +1, then the actual reading, one reading is -2, another reading is +5, -3, and so on. That cancels out eventually if you stack multiple images on top of each other. So you can see here, this is Andromeda Galaxy. There's almost nothing visible when we take a normal photo, and people might get discouraged saying, what is this? I got nothing. Whereas when you stack it, this is what you get. You get a beautiful image. You get multiple layers of the Andromeda Galaxy. You also get this other small galaxy that you can see here, right? Which is almost not visible when you had it before. this is just from the stacking. But what about the noise that is not random, right? So this is random noise, and this signal to noise ratio increases as the square root of n. So we try to increase the signal to noise ratio. And the way to do that is taking more and more images, and as we take more images, it increases the square root of the number of images. So SNR is basically proportional to the root of n. So if you take 100 images, your SNR will be 10 times better, right? Now, after stacking, there's other stuff you have to do, which means this is the light frame. So light frame essentially captures what kind of the objects that you're basically capturing. So this is the main thing. This is light frame, and let's say your ISO, or ISO effectively represents your pixel sensitivity to light. It's like an amplification factor. So if one volt is received, or 1 coulomb of charge received, it's converted to 1 volt. Should the reading be 100 or should the reading be 150 when you finally calculate the pixel value, right? So that is given by the ISO. So there's also the exposure time, which means how long you left your camera over. So let's say the ISO is 800 and exposure time is 480 seconds. For the Andromeda Galaxy, this is probably very much accurate. And you want to minimize on all the other types of noise that are not just random. One of those is a dark frame. So the dark frame takes into account the noise that comes from the camera sensor heating up. Now you've left your camera on for 480 seconds at 800 ISO. It's an electronic device. Obviously, the camera sensor is bound to heat up. That heating up causes some amount of noise. So when you read out the value, it won't be exactly that as what you think it might be. Ideally, what it should be. So here I've the dark frame has been basically enhanced so that you can see what it looks like, but in reality, it won't be so obvious. Like here you can see like this clear redness here, and at the corners especially. In practical use, it won't be so apparent, but here it is. I've tried to make sure that you can see the full effect. And basically, this is a very big problem because when you leave it on for long times, you will be facing this issue. And effectively, you have to subtract this value so that you negate the effect of your camera sensor heating up. How do you take this dark frame? Very simple. Just put a lid on your camera, and with the exact same ISO and exact same exposure, take a shot. Effectively, that gives a dark noise because you don't want any light frame. You don't want anything. You want a perfectly black screen, and you want to take the value that comes just from your camera sensor heating up. Okay. There's also the bias frame. The bias frame tells you what is your camera readout noise. So when your sensor is trying to read out a value, there is some noise associated with that also. Because again, nobody's coming and whispering this value in your ear, right? You have to measure this value. When your camera tries to read out this signal, it again adds some pixel value. That is the bias noise or the bias frame. And because you're trying to measure only the readout noise, you're not trying to measure the noise from how hot your sensor gets, just how much, just the value that it's reading out. Some noise will be added to that. Exposure time should be as low as possible. So 1/4000 of a second if possible, even lower. But as low as your camera gets is better. But the ISO should be the same. And the way to do this, same. Just put a lid on your camera and take a photo of as short of an exposure time as possible. This gives you your camera readout noise. So bias frame is also called readout noise. And there's again the photo here. It looks like there's a lot of noise. Again, this is amplified by some factor for display purposes to show what kind of a thing you'll be looking at. And there's also the flat frame. So what is a flat frame? People who might be doing normal photography, does anyone know what vignetting is? Vignetting. Does anyone know what vignetting is?
Yeah, it means basically we are darkening the edges and
Yeah,
yeah.
yeah, exactly. So basically what happens is when you take a photo of anything, mostly inherently because of the optical light path, the um, camera sensor is not evenly illuminated. So rather the field is not evenly illuminated. It's called uneven field illumination, which means because of the optical light path, the edges appear to be darker than what they should be. So here you can clearly see, again, this is amplified, but this is kind of what it looks like. The edges are clearly darker than the center, even though it should not be like that. It should be perfectly white because the light source is perfectly illuminating the camera, the camera sensor, but it's not being illuminated perfectly. This means there's a problem, and that is captured by the flat frame. This also captures some amount of smudges or dust on your camera sensor. In case the light path is being obstructed by something, that also gets captured. So that captures the flat frame. And this is again taken, so I made a mistake, the lens is not closed. You put a white t-shirt or any sort of white cloth on your camera sensor or your camera lens, and use like a torch or the sun, something like that, and capture the photo. Exposure time doesn't really matter. What you're looking at is just the ratio of the values that you get at the center to that of the edges, because that's what you're really trying to fix. You don't care about the absolute values, you just care about the ratio at the center to that of the edges. So exposure time doesn't really matter. It mostly just matters that you get a good color calibration, that you get the image that you really want. So even if it's a little bit like it's not perfectly white, it doesn't matter. But in case your exposure time is a little bit high, a few seconds maybe, for some reason um, you weren't able to get short exposure, there's something called dark flats also, which I've not included here. But dark flats essentially mean if your flats are of lot of exposure, there is dark noise and capturing that also. So dark flats are taken to make sure that the dark noise in the flat frames are removed. Now this seems obviously very um, so to say unnecessary, and it's much work, which it kind of is. But if you really want proper clean flat frames, you should consider removing the dark noise even from your flat frames. That's only if you're taking a decent exposure of your flats. So these are your calibration frames. These frames are called calibration frames. The lights, darks, bias, flats, dark flats. But I have one question for you guys. This is in the assignment, which has not been uploaded yet, but we'll upload it soon. We're capturing the dark frame, right? Now, when we capture the dark frame, it's 480 seconds. So in the start, let's say the readout noise comes in 1 by 8,000 of a second. Even when they're reading out the first pixel value, some readout noise will be there, right? Are we not already capturing the readout noise in this dark frame? Why again must we capture this bias frame? Why this exposure time of such a small time? Why do we even need to capture it when we're already capturing a dark frame that has captured the readout noise? Does anyone have any idea why we do this? Why do we need a bias frame even though we already have a dark frame that captures the readout noise? First of all, does the dark frame even capture the readout noise? Does it even do that?
Hello, sir.
Yeah, tell me.
Sir, how can we pick up a photo of dark frame? So, um, if we cover the hand on camera, then also dark frame also can come. No, this dark frame scene on camera.
The thing is, your hand is not the best. You would probably just use something that is perfectly opaque. And the thing with your hand is your hand might move, right? So you won't keep your hand perfectly still for minutes on minutes on end. So 480 seconds is what? Like 8 minutes. You're telling me you're gonna keep your hand perfectly still? Probably not, right? You just put the camera lens ka lid
I have
on.
al-
You put the lid
Sir,
on
I
and
have
it's perfectly done.
Sir, I have tried at home earlier. So by putting hand on camera only, sir, this type of frame was came also on my camera.
The thing is,
Hand
it
only.
might have come, but it might be accurate. That's the thing.
Okay, sir.
Like, you understand what I'm saying, right? It might not be perfectly accurate
Hi, sir. Hello.
because your hand is moving, right? Like you want it such that no light is coming onto the camera sensor, but your hand is moving a little bit, and you're not going to keep it perfectly still. So because of the movement of your hand, the values will be affected a little bit, right? Because think about what you're trying to capture in a dark frame. In dark frame, you're capturing the thermal noise. You don't want to capture anything else except except the noise that comes from the camera sensor heating up. That's all you want. You don't want any external noise. So the more like still an object is perfectly black, the better. So if you can cover it with perfectly black chart paper, go ahead. But a lens already does that, right? Like a camera lid, sorry, a camera lid already does that.
Sir, what does ISO 800 signifies?
So ISO signifies how much like your pixel values are amplified by how sensitive your pixels are to light. So effectively, it's like, let's say 1 coulomb of charge is collected in your pixel, right? Or 1 volt is out. So pixel values go from 0 to 256. Like RGB values go from 0 to 256, right? Now,
Yes, sir.
does 1 volt represent, like 1 volt should represent 256, or should 1 volt represent 128? How do you know that? How does your camera sensor or pixel know ki 1 volt means that this is the maximum amount of light that can be, come into the sensor? Or does it know ki, okay, this is about halfway of the maximum? That is governed by the ISO. So it tells you if you have a certain reading, what does that correspond to in terms of pixel values?
Okay, sir. And exposure time, what about? Like,
So exposure time just means how long your camera sensor is open for, or how long you're shooting. So when you take a photo of, let's say I'm taking a photo of your face, right? I say smile. Now that's a very small snapshot, 1 by 480th, 60th of a second, 30th, 1 by 30th of a second, something like that, right? Very, very small exposure, which means the amount of time my pixels are being illuminated to light is very less. है ना? But when it comes to astrophotography, when I'm looking at, let's say, the Andromeda galaxy, that is not enough, right? You can see in this picture, this is clearly not, and this is very long exposure, by the way. But uh, so to say that even with long exposures, you won't get uh, all the light that you need because they're so far away. Leaving the camera on for a small amount of time is not enough. So you have to leave the camera on for a very long amount of time and let the sensor take all the details in the night sky, so to say. So the exposure time basically
okay,
means
thank
how
you.
long your sensor is on. Yeah. So coming back to this, the main thing is that does anyone um have an idea of why we take a dark frame and then again take a bias frame? It doesn't make sense to subtract it twice, right? If we're subtracting it twice, we're literally double counting. We don't want to double count. So either we take bias or dark frame. But why do we have to take both of them? If anyone has any ideas, let me know. Otherwise, we can move on. I mean, this is a question in your assignment, so you guys should research about it. Have a look at.
Are we going to subtract the light frame as well? Sorry,
No,
sorry,
no, no. The
not the
light frame.
light frame, the flat frame.
Yeah, we're gonna subtract the flats. Yeah.
So the flat
I mean,
frame
not
will also
exactly
capture
subtracted.
bias noise.
Yeah, exactly.
So
That's also
that's
there.
why we need the bias frame so that we can add it because the bias noise will be subtracted twice, so we should add it.
So, um, sorry, can you come again? Can you come again? Sorry.
Uh,
I said that as we are subtracting dark frame as well as light frame, so the bias noise will be subtracted twice. So we should add the bias frame to get everything balanced.
Like that. So it's kind of like that. Um, in the sense that uh, like you're close to the answer, but it's not exactly that. It's that see the thing is with flats, no, we don't exactly subtract the flats because you're trying to make sure that these edges are evenly illuminated, है ना? Because these edges are say these right now this edge value is lesser than this value. The pixel value here is much less than the value here, and you're trying to say that I want it such that this entire field has the exact same value. I don't want my edges to have lower values in my center. If you just subtract the flat frames directly, you don't capture that. You don't capture what you're trying to get, right? So flat frames are not exactly subtracted directly. So flat frames are there's something else to do with them. But you're right in the sense that bias frames are not subtracted. We would be double counting. So the exact math behind stacking is a little bit different from what you might think. The dark frames are subtracted, but the bias and flats, they're not directly subtracted. Otherwise, we would not get the correct output or what the desired output would be, right? So they're not exactly subtracted directly. Otherwise, we would be double counting, yes. So that brings us to the end of the stacking and astrophotography and all that. We'll talk a little bit about the sensors that we were talking so much about.
Hello, sir.
So there's two types of, sorry. Yeah.
Sir, one question. Sir, can you repeat once again these answers? So that subtraction of bias frames and dark frames. Once again.
Yeah. So the thing is, from the light frames, we do subtract the dark frames, but if we subtract the bias, we would be double counting. And we're also not subtracting the flats because think about why we're putting the flats, right? These edges are appear to be darker than the center, even though it's not like that. The sensor is being like the field is actually perfectly illuminated, but it's appearing so that the edges are darker. Now, this is with the optical path of the light that's being taken, right? So we want to make sure that these edges, like in the flat frame, we're trying to fix the fact that the edges are darker than they appear. How do we do that? Well, the solution is definitely not to subtract directly from the light frame, right? If you subtract directly from the light frame, you would not achieve much. Um, Hence, the flats are not directly subtracted. There is some a little bit other kind of math that's done, um, and neither is the bias frame directly subtracted. So bias frame also is not directly subtracted. Otherwise, you would actually be double counting. Yeah.
Thank you, sir.
Okay. So coming to CCD and CMOS. So these are the two types of sensors that you'll have on your camera. So when you get any camera, mostly it's one of these two. CMOS stands for complementary metal oxide semiconductor, and CCD stands for charge coupled device. 1 second. Okay, right. So first we look at the CMOS sensor because that's very simple. So um, the way these sensors work is there are individual pixels laid out in like this grid format, right? This individual pixels laid out in this grid format, and um, how does this work? Well, as each, like let's say photons are, I'm sure everyone knows about the photoelectric effect, right? So as photons um, hit a metal plate, some electrons are emitted, and basically you're trying to measure, okay, how much charge, how many electrons are being emitted or stored. So if you have some amount of charge, what voltage does that correspond to, and what that voltage, how much pixel value does that correspond to, right? So if you have, let's say, 1 coulomb of charge, that should correspond to about 1 volts. And if you have 2 coulomb of charge, ideally it should be exactly 2 volts. So in a CMOS sensor, this 1 coulomb of charge to 1 volt happens at the pixel location itself. So that pixel only converts from uh, 1 coulomb from charge to voltage, sort of. It reads out the value. The amplification happens later, but the readout of the value at the pixel happens at that pixel itself in a CMOS sensor. So if you have a look at it, so as you saw, the charge was immediately read out, right? You say 0.7, 3.6, 3.6, 1.4, whatever. Sorry. And this is the amplification factor. So when you have, let's say, 0.7 volt, what should be the pixel value that is given by the amplification factor, ISO, whatever you want to call it, right? So this is the CMOS sensor. Now, this is relatively easy to implement because you're just reading out the pixel value, and then after that pixel value is read out, you're saying, okay, fine, this job is done. Now we'll go on and amplify it by some factor. Okay, fair enough. Whereas in a CCD sensor, you don't have that. So in a CCD, what happens is once charge is stored, that charge is not immediately read out to some value. Yes, that readout happens at one specific place and that specific place only. So you can see, um, look at how the charge moves from one cell to another, and at this location is when the readout happens, right? So the charge moves one by one, and realistically happens array from array by array, right? So effectively in a CCD sensor, the charge is read out at one point and one point only. Then after the value is read out, the amplification process is the same. So that's why a CCD is different from a CMOS sensor. Now, can anyone think of a reason why would this CCD sensor be better than a CMOS sensor? Like, why is it useful to read out at one location and not read out at individual locations by themselves? What is the difference and why is CCD better? Can anyone think of a reason?
Hello.
Yeah.
So I think in CCD, because we have the application or the sorry, we have the readout process taking place at each individual pixel. There is a high susceptibility to noise in CCD. Uh,
Hmm.
sorry, in CMOS, my bad.
Yeah.
In CCD, because the readout process takes place in one specific spot, it is more controllable and it is less susceptible to noise.
Right. Yeah, exactly. So that's exactly correct. Because the CMOS sensor has its pixel um, reading out at that location itself. If the readout machine is slightly incorrect in the sense that it amplifies by some factor, let's say all pixels are evenly illuminated by 1 volts, by the same amount of charge rather. So every cell, every pixel in the CMOS sensor has 1 coulomb of charge, right? Perfectly 1 coulomb, no plus minus anything. One pixel might read out exactly one pixel might read out 0.99, one might read out 1.01, one might read out 1.05, one might read out 0.95. These are all errors that add up, right? Not as um, apparent as what I've said, but these are present. And in a CCD, this is not there. If 1 coulomb of charge has hit or is stored in that pixel, when it's read out by the same readout machine, right? So whether it's uh, 1 coulomb of charge becoming 0.99 or 1 coulomb of charge becoming 1.01, it's still the same for all of them. Everything will be 1.01 or everything will be 0.99. So that way, that noise or that difference between pixel to pixel values, that is almost entirely absent in CCD. And that's why CCDs are much better for deep sky astrophotography, especially when you want longer exposures, when this phenomenon is more and more apparent, right? There is also a problem with CCD. It's that the thing is, these equipments are very expensive to make. Obviously, when it comes to making equipment where you're transferring the charge one by one, and you have this readout machine, you have to get the charge till there. That takes some expensive equipment, and it's not for normal astrophotography. Sorry, for normal photography. It's only for astrophotography. Also, the readout takes a while. It's not instantaneous, and because this readout takes a while, it might frustrate some people. But that is the smaller issue. The main issue is that it takes a lot of money to buy these sensors and make them. The material is also more expensive, etc. So, with the end of this explanation of the sensors, we've come to an end to the first session. I hope you guys enjoyed it and learned something new. Learned about the night sky, how to capture it, telescopes, camera sensors, everything there is to know about dealing with observational astronomy and a little bit about astrophotography. I hope you guys had fun. For attendance, please scan this QR code. You can take a photo of it and do it later. Please scan this QR code, and after you're done, upload it, or it's a Google Form link. Just put your contact details and everything, and your attendance will be recorded. So yeah, thank you guys for attending this session. I think the next 5 minutes
So
we'll end the meeting.
the QR is actually for the feedback. We'll be sharing link for the attendance
Oh,
form in the channel. Please will go for.
oh, sorry. Yeah, this is the feedback link, my bad. Oh, I'm sorry. There are so many questions in the chat. Nobody read it out. Uh, okay, I'll just quickly answer some of the questions that are on in the chat. Uh, so Swastika your question was, should I try to clean it again? Try to clean it, but if it's blur and smudge, then everything, then you might want to get either a different cleaning set or probably try and just get a new scope. It might be pretty old, I'm sure, 2 years. So try and get a new scope maybe, or try to use different cleaning equipment. Could you explain why a larger field of view needs a smaller focal length telescope? So this basically is very simple to understand. I didn't explain it because it would get complicated, but um, you can have a look on the internet. It's just like I think in this slide I kind of explained it, but not too much. This slide, right? Yeah. So here you can see, like, let's say light is coming from the edges. This green light is kind of from the edges, and the purple rays is from the center. You can kind of imagine that um, the amount of like distance between the 2 points, like the focal point of the green light and the purple light, is slightly different, right? So green light would be somewhere here and the purple light would be somewhere here. So because of that difference, you can, like, the angular width that you see in the sky varies, and that is a function of the focal length of the telescope. And it so happens that as the focal length is higher, these points are farther and farther away. So because these points are farther and farther away, even if the light is very, very close to this purple line, so in this case, green light is close to the purple light, right? Still, even though it's so close, because the focal length is large, you're kind of limiting your vision by just the green light, even though it's close. Whereas if it was a shorter focal length, the more amount of light, so a light ray is even lesser, even lower than the green light, hitting the exact same place, would be able to capture in this eyepiece. That's kind of how it works. Is your altitude measured from the horizon? Yes. But doesn't the sun revolve around Sagittarius A? Yep, it does. But like Vedanshu said, the thing is, this motion is very, 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 very slow. Even the Earth revolves around the sun, right? But the thing is, that difference, like, first of all, the movement around Sagittarius A is very slow. You might also say the Earth revolves around the sun, so RA index should change. But that parallax is very, very, very small in comparison to how far away the stars are. The stars are light years, hundreds of light years, thousands of light years far away, right? But still, we can see them at almost the exact same place in the sky. Do you get assignments? Yes, you will have an assignment. PPT with the, yeah, I'll send the PPT after this. Noise, what do I mean by noise? Noise is external unwanted light that is captured. So, like Abhishek said, so basically it's like you have other stars in the field also, right? You have other objects. You have your light path gets so to say shifted here and there a little bit. So sometimes your light will hit an dust particle in the, like a ray of light will hit a dust particle and get reflected somewhere or deflected, right? Something like that. So all that noise, even from random objects in the sky, that is captured by the noise. More than random dots and pixels, it's like it doesn't look like random dots and pixels. It's like the pixel values themselves fluctuate a little bit. So instead of 175, let's say, it would be 174, 173, 177, such as that. Yeah. Yeah, all of you have talked about vignetting correctly. Nice. No, it's not the camera software. It is because of the optical light path. Like it's not able to reach the sensor properly. Well, but the thing is, sensors, like modern sensors, are equipped to combat it. Like they try to make sure that it's not the case is not such that the edges are dark. Camera sensors do that. No, CCD would not be cost effective. CCD is more um, inefficient to make because the material and all of that is pretty hard. Yeah, exactly. CCD's readout will have a systematic error which can be eliminated, whereas CMOS will have compounded errors, and these are hard to get rid of. What may happen when the Milky Way and Andromeda collide? Uh, you would see explosions of um, you would see very bright collision, and there's a video that Vsauce, if you know Vsauce made a video about it. It's called what what is it called? It's like What We Will Miss or something like that. I think it's called What We Will Miss by Vsauce. He talks about the collision between Andromeda and Milky Way. It'll be a beautiful collision. Like a lot of new stars will be born, a lot of um, interactions at the very least. Yeah, the class is over. If you guys want to leave, I'm just answering like questions. I had a very basic version of a telescope. How do I capture the image with my phone? Um, you can like effectively you have to mount your phone on it. Oh, you want to capture like that? Okay, okay. So basically, there are some adapters, not adapters, but like small like uh tool that helps you mount your phone on telescopes. Now your telescope might not be compatible, but the telescope we have, at least at our HSB rooftop, is very well compatible with that tool. So we just attach the phone and mount that phone with the use of that tool onto the telescope. So that allows us to capture night sky. You might have to look into whether that's possible or not. But considering you're saying very basic, I don't think so. You would probably be better off just using your phone directly. What software can be used to stack? So there's multiple softwares. Um, so Cyril is one of them. Deep Sky Stacking is one of them. You can have a look. And yeah. Yeah, you can leave the session. It's over. If people have doubts, you can ask. I heard that space is expanding and everything is spreading apart from each other. So why is Andromeda approaching Milky Way? So that way, why is the Earth revolving around the sun? Everything is spreading. So why are we stationary on the Earth? So there is a factor of expansion and there's a factor of gravity, right? So space might be expanding. things might be moving farther, but some things are locally moving closer than they are moving farther, right? Imagine how big the Milky Way and the Andromeda galaxy are. They're thousands of light years apart. Their gravity is enormous, right? And that kind of combats the expansion of space, so to say. So things are moving apart, yes, but they are also things are also moving together because of gravity. Can you please provide a sorry. Yeah, Shrijan studied online. You have a question? Go ahead. Dhruv Gandhi, I'm not able to see your question. 1 second. It's on 12:35. Can you provide a bit more information regarding the assignments? So there'll be like a few questions. Like I don't know exactly how many questions I'll put, but there'll be a few questions, and you'll have to submit the answers somewhere. I'm not exactly sure. We'll let you know of the exact procedure, but there'll be like about 10 or so questions, 10 to 12 questions, and you'll have to just solve them, look it up, write the answers. Solve. How is infrared and UV sensors different from visible ones? Are they the same? So, not exact. That's not how it works. Like, there's no sensors as such. It's just, so let's talk about a monochrome camera. Okay, it can just detect the intensity of light. What you would do is, monochrome camera can only detect the intensity of light. So it just tells you like, okay, this much light is falling. That's it. Now, you can put filters on top of your camera and say, okay, this only red light should pass. So you put a red filter and say only red light should pass. Okay, then your camera sensors measures only the red light and says, okay, the red value is this much. Then you do the same with blue, green, right? So then with blue and green also your sensor now picked up the values and your camera knows, okay, the blue values for this pixel was this, green value for the pixel was this, and red value for the pixel was this. The same way you have these like those kind of what do you say, filters that can filter out only specific frequencies of light, and you can figure out, okay, this is infrared and this is UV, whatever. And sometimes what astronomers do, astrophotographers do, is they'll artificially color this infrared or UV light to bring out some details that are not visible in that normal sky. Yeah, no problem. Okay, I think we'll end the session now. If anyone has any questions, okay, last question. Like black hole, I heard something as white hole. Does it exist? People don't know. They only hypothesize. But probably not. Yeah, no problem. Hope you guys learned something nice, had fun. And yeah, wormhole. I know that's all hypothesized, but no one has confirmed anything yet. Probably doesn't exist. Okay, so we'll end it now. If anyone has any other questions, please DM in the WhatsApp group, and I'll try to answer as many as I can. All right then. See you. Bye bye, guys. Hope you had fun.